for inviting me here, Greg, and that very kind introduction. It saves me having to repeat it, so I won't. If I use words that you don't quite understand, raise your paw. I've only been here 2 years. I've kind of acclimatized or acclimated. We'll get there. That's the last of the jokes. I got involved in 3D printing 2 years ago when I came to Silicon Valley because I wanted to surf. And I was trying to work out which technology was going to be big. And being a venture capitalist, and there's more VCs around here than you wave a stick at, you know, you've got to kind of carve out a position for yourself. And though I backed companies in the UK that were in the 2D to 3D utility plugins in the visual effects market and also plugins to CAD. So I had been following this sector for some time. And being a mech engineer around here actually has some kudos when you talk about 3D printing, though, you know, my experience in real mech eng isn't really a great deal other than degree. I was in the army where I built shit and blew shit up. So, you know, that's a good way to work out how things go together.
Which one of those is more fun?
Oh, blowing shit up. But the problem is, when you were training, because, you know, fortunately I was not in active combat, you always had to rebuild it. Yeah, because you got the other training group behind you that they want to blow it up as well. And then, so, but my God, I've got some stories about explosives, but got to be careful. Yes, my business. What do? I'm a VAR in Silicon Valley, and I resell a whole host of 3D printing technologies. You know, scanning, software, printers, and this is a way for me to kind of educate myself in what all this technology is about. Because it's more than just the printer. Everyone thinks of a printer, and it's much more than a 3D printer, of course. It's more than that. So just a kind of little bit of a plug on scanning, which I think is very underrated. You know, I'll come on to later how many 3D printers are in the world, types of, but you know, creating content, you know, from scanning is not as well talked about, not as much talked about. So we've got a very good low-cost scanner at the back that I'd welcome everyone to go and have a look at. But without further ado, on to the most important thing, 3D printing, because it does bring things together. It was invented in '84. What was happening in '84? I played this as a kid on the BBC Basic. It's called Chucky Egg. Anyone else play that game? Yeah, fantastic, wasn't it? What else was in the Atari? This came out, and the first autonomous car. And of course, you know, that computer, which is so famous now, that chap who was just so innovative. So, you know, it's been around a long time. That's the message that I want to kind of get across. And, you know, what is it? You know, I did a presentation in Cupertino Library a few weeks ago, and at the end of it, I was asked, well, what is 3D printing? I don't understand it, so let me be clear. It is making a physical object from a three-dimensional model, a digital model. And you basically layer after layer. You know, I think that's pretty clear. If it's not, put your hand up, I'll say exactly the same thing again. So, you know, you get into a model and then your XYZ motors and that's what you do. And these are the 5 types of technologies. I do not want to go into detail because that's far too much. But most people are familiar with extrusion. That's what you see at the back. Basically thermoplastic, you're putting through a little hole, you're controlling a bunch of motors, making sure it goes in the right place. Granular is when you're kind of gluing or sintering with a laser a bed of powder, and then you're repeating the same process, bringing that digital model every layer, and you're using either a glue or you're using a laser to kind of connect the particles together. Often there's post-processing that you might have to fire it up and clean it up afterwards. These things do not come out of the machine ready. Yeah. Light polymerization is where you're using a photopolymer and either a kind of blue light or white light, or using a laser to cause the molecules to solidify in that particular space that you wanted to. Yeah. Lamination. One example of lamination is paper. This is me in paper, which I will pass around. Don't take me away. And I've got some other examples of paper here. And plastic. So this is ABS, but it's in an interesting structure, which I will come on to later. The other technology, electrode deposition, which is well used in the semiconductor industry. There's a great company a million miles away from here in Southern California called Microfabrica, which is creating medical devices, biopsy devices using this technology, and it's sub a millimeter, and you can put it into veins, and it actually works. It's fantastic, and it's already touching our lives today. By noon, loads of things that you see around the house have been in some way, predominantly prototype, connected with 3D printing process, because it allows you to get products to market that much quicker. And if you look at other types of products, we're manufacturing them. How many of you guys are familiar with Invisalign? I think everyone is. It's a great marketing machine. Based in Santa Clara. It's 3D printed. Not that anyone really cares about that, do they? Not at all. 95% of the in-the-ear hearing aids are 3D printed. GE, that's a funny little thing that you probably don't know what it is. That's a fuel nozzle for a jet engine. It's 3D printed. Artificial limbs. It's a company in San Francisco called Bespoke Innovation, purchased by 3D Systems. It's doing a lot of work in that space. 28 million parts in 2012, 3D printed. Principally aerospace, medical, and dental. So, high value goods already is being used, because the great thing about 3D printing is you can create things that you can't make in other ways, and you can make them very personalised. That's where scanning comes in. When they do the in-the-ear hearing aids, what they do, they pop the gunk into your ear, take it out when it hardens, and then they scan it, and then they use some software to make sure that the holes are best suited for optimal acoustics, and you just can't make that in a traditional way, because you cannot create a round hole, a curved hole, I think it's, or a helix, in traditional manufacturing technology. So, what materials can you print in? Everyone recognises Yoda, metals, paper, sugar. Someone asked about sugar earlier on, that you can print in sugar. Why you'd want to do it, I suppose if you're a high-end cafe, why not? Chocolate, any Japanese folk in the audience? Anyone know what you do Valentine's Day in Japan? Give chocolates to your man. And so what they did, they scanned faces, made silicon molds, and did chocolates. And these sorts of things that you do hear about, like you hear about the gun being printed. They kind of hit the news and don't really go anywhere. These are not high-value products. Ceramics. Bottom right is ceramics that you use a kind of granular type technology, and then you fire it up as you would fire a traditional ceramic. Go from green to end stage. Yes?
You said you do 3D printing with metal?
Yes.
So how does that work?
Laser sintering or electron beam. It's granular. So you're pretty much putting a powder layer down, and then you're controlling the laser to not only sinter where you want the model to be, but you also need a lot of support structure because it's quite a violent process, and it's done in an argon gas. Because there was a interesting one a few years ago, it's called Loma, that you used laser to cut paper. And of course there was a few fires. Yeah. And it's similar to the M-Core, which is paper, that uses a knife, which is a little bit safer. But yeah, it's an interesting one. But there's hosts. I've got some more materials here, and these are super expensive. Hence the reason they are in a case. I'll keep that one back because I've got a picture of that later. But this is ceramic, aluminium oxide, 99.4% dense. So, and this is produced by the DLP process where you grow it out of a slurry, almost like you grow a crystal this way up. This kind of comes out of a slurry using a photopolymer to create the green, and then you fire it, and it can withstand 1,000 degrees centigrade. They're actually, those pieces I'm passing around are actually medical scripts. So, where are we today? Who would like to hazard a guess? Any guessing?
Oh,
God, we've got some smart people in the audience. Okay. I think we're roughly around about there. You know, there's probably some guys in the audience that don't really remember this stuff. I was in Copenhagen and Munich last week, so I'm not quite sure where I am. You're right. You can draw a lot of similarities between historical technology curves and. I've been pushed out on the limb, which often I am, and I'm pretty bullish in what I say. I'd put us in the late 70s if you were to compare us with the PC industry. I think I've got some evidence for that, but I'll come on to this in a moment. The words are not important, actually, but you can read them because they're pretty interesting. But we talk about the third revolution. Yeah, so be it. Since we started to kind of make things in a slightly different way to what we made them before, we've been using mechanical processes, and now today we're using a lot of software, electronics, all that sort of. It's great stuff to come up with products that we can fit in our pocket, and we can, just do so much, which is incredible. But if you put things into perspective, in the life of us, it's only recently we've been making things the way that we have been making them. And if you look at, that's kind of the kind of Reformation period. So, my point being is, we haven't always made things the way we have done, and that's what always interested me about 3D printing, and in particular structures, and how structures and materials have come together to do things that which can really change the world. So the reality check is that there's less than 100,000 desktop printers in the world. And there's about 100,000 or less commercial 3D printers in the world. I think that they kind of crossed over about 12 months ago, as in more desktops than commercial 3D printers. And the desktop market is growing at 200 to 400%, whoever you want to listen to and agree. With the likes of HP coming into the market, which is not a secret, is it? No, it's been spoken about for quite some time. I think that's really good. Autodesk now coming into the market, because what the desktop technology is missing, which is not only a purpose, because I don't believe it really has a purpose, it's a solution seeking, or it's seeking a solution to a problem, that we need to lower costs, improve quality, get reliability up, etc., and create that reason why somebody would buy a desktop printer. And this is why I think people at home will buy a desktop printer. And just to kind of put that peg in the sand, the VIC-20, launched in 1980, was the first computer to sell over 1 million units. And I think, you know, the principal reason why people bought that was gaming and education. I had my first computer back in 83, BBC Basic, bought for me for education. I played games on it. And I think that's going to be the route that will take this into the home. So I want to now move on to, unless anyone has any questions or comments, I'm quite happy to take them at this stage. I'll move on to the second half of the presentation. Any? Yes?
Did you say what the difference between like desktop and commercial?
Cost.
Just cost.
And quality of output. Typically they say the
Is there a big gap between, or?
Often it's spoken as sub 5,000 and over 5,000. So they kind of put that 5,000 mark. But, you know, the MakerBot 2 or the Formlab, which is, you know, that $2,000 to $3,000 mark, you know, often it's small businesses buying them. You know, to really be consumer, I think you've got to go sub $500, and we're not there yet. On the commercial printer side, you know, for example, the printer that did these ceramics is like $300,000. You're looking at a concept laser, it's about $1 million, which does metals. And you know, the cost of acquisition is very different to the cost of ownership, because of course you need to have a lot of additional assets, high energy cost, material cost. It's very difficult to get operators, especially around, say, Silicon Valley, where there's not a history of aerospace if you're looking at metals, for example. So, you know, costs are certainly coming down, and they've been coming down rapidly over the last 5 years. You know, they would cost typically a commercial printer over $20,000, $50,000, and yet you get decent Stratasys or 3D systems and many others sub 20. Yes. Yes.
For metal 3D printing, you said that they use an electron beam.
A what, sorry?
Electron beam or a laser.
Laser. Yes.
Laser.
Yeah. In a argon gas. Yes.
Quick question on the electron deposition. Is that high voltage?
Got no idea.
You had it at the last...
Yes, I've got no idea whether it's high or low voltage.
Oh, okay.
Yeah, I presume it's the same voltage they use in the semiconductor industry,
Okay.
because it is that technology.
I've seen like a presentation where they have like very hard metals to work with, making some rocket nozzles, and just using some very high voltage here and working with NASA on this, like some titanium and everything.
Yeah, I'm not aware of that. I wouldn't be surprised. And you know, NASA are doing some interesting things, as are the other national laboratories, Livermore in particular, and also Oak Ridge. They're doing a vast amount of work using, you know, polymers as well as metals. Okay. Yes, on to where structures and materials collide, form and function. This is what really excites me, though I may not look as if I'm excited. I'm really excited about this, truly, because it gets onto biomimicry, and this is really cool. Nature uses very few materials. It uses structures instead. I think this is widely known. If not, I've told you. So you can remember that fact. Anyone like to hazard a guess as to what that is?
Galaxy or the brain?
It's galaxies, well done. Most people say the brain straight off. Yeah? Which is an interesting kind of structure. I won't ask folk what that is, because I think we all kind of know. Bone, yeah, I don't know what bone. It's not totally important, but you know, same material, principally. Yeah, structure for a variety of reasons. Outside strength, inside to allow fluid flow. So that's pretty cool. Fly, dragonfly. Notice the structures on the wing, which gives it some interesting properties, which allows it to fly magically. Built up over millions of years of evolution. The butterfly. Anyone like to tell me what's special about this and structure? Smart people, isn't it? Who's that? What's that? Anyone? Anyone know how much blue pigmentation is in the wing? Yeah. And this is pretty good. I think in the future we'll be using structures to do colours. This is far out stuff. So we look as structures enable new materials, and indeed structures are new materials. And when we look at function, form and material, tying it into 3D printing, we look at 3D printing, digital modelling, material theory. And bringing those two together, we can do some really quite interesting things. Some people will be familiar with this graph, especially those that have done mech-eng, one chap in the room at least. The interesting thing is, we can use structures to get out of that, or get into the holes, get out of that straight line. And that means you can do a lot of interesting things.
I'm a software guy. What the heck are the two axes?
Oh, right, density, Young's module, elasticity. Young's module is this English chap had nothing to do, so he plotted all these materials, and he found a correlation that most materials are do fall in certain areas. So, for example, you've got at the bottom flexible polymers, and at the top you've got alloys and steel, and they tend to form and sit in that kind of runway. Whereas if we can move out of those areas, we can create some very interesting structures that can do things which might have inverse correlations, so that, for example, you pull it and it gets bigger, or you push it and it gets smaller, or a whole host of things that you can do with structures. So 3D printing allows us to manipulate materials to almost change their properties. So you look at a structure as if it is a different material. So that's the point of getting out of this area where it's already occupied with materials. Yes?
I think metamaterials is the term used for that, where you have normal structures you're used to looking at, but when arranged in a specific way, they affect a very different effect through that material.
Yeah. And what 3D printing allows you to do is, because the way that you can create structures, you can do that and more.
Yeah.
For example, you restructure, and here's an example. These are all the same materials, yet they've got very different properties. They're all nylon. These are just very simple examples. And at the moment, 3D printing has its limitations. You can't go as low as you might want in resolution. It's one thing that we haven't worked out is, what is the Moore's law? Is it resolution? Is it speed? Is it a combination thereof? That, we can, at the moment, going down to sub-100 micron feature is not the norm. There's a few exceptions like the microfabrica with electron deposition type technology, but there are laboratories at the moment that are working significantly below the micron level, which we can't talk about. So, with materials and using structures, nylon, for example, you can have a bendy material. What it is, normally nylon is pretty hard if you laser sinter it, and you can have different. You can design structures so that they perform in a certain way. For example, you can imagine this in a car, whereby it would crumple at a certain pressure, certain force, and you could change that according to where it was in the car by changing the structure, as an example. It would be a very expensive car, like this, which is a concept Audi, built in Germany, near Nuremberg, for Audi, and this was all 3D printed. And in using structures rather than just printing it as a solid body, you had significant weight reduction. You had significant material reduction. But you also had other benefits of design. I thought it's quite a nice looking car. It is longer in certain instances to build, but the benefits could outweigh the fact it might take longer. Another example, without some stats, is this gearbox, which has been designed to two reasons. Save weight, very important, because less weight, less fuel, but also designed to have the right thermal conductive efficiency that optimizes that equipment, or that piece of a car, which is just not commercially viable today. But you know, often a lot of things aren't, hence why the technology is at the higher value goods like aerospace and medical devices. The top pictures here are molds. So I think a lot of traditional manufacturing is going to be improved significantly by using additive manufacturing, because you can see in there that there are channels, vertical channels, and they are designed so that you can inject air in to cool it quicker, and the lattice structure is designed to, you know, take the heat out of the product that you're trying to get from the production process, and it can therefore speed up production, so you can bring costs down. It might be more expensive to buy this mold, but it means you can create more faster. So it has its benefits. The bottom one, anyone would like to guess what that is? I know it's a spoon, but what type of spoon?
Steel ladle?
No, it's an ice cream spoon. So the ice cream doesn't stick. Anyone want to know how much it cost? About $5,000. So you go and have an ice cream shop in a very good location to be able to pay for that spoon. But I suppose if you did a work and time motion analysis on it, it might be worth it. I've not done it. A few other examples. This is a hip replacement cap. And it's actually designed specifically so that it kind of replicates the bone structure, so that the tissues grow into it. And the bottom left is a screw, and the bottom right is a skull cap. And it's used extensively in medical in these cases, and it's going to be used more and more. This is something that Oak Ridge National Laboratory did. They wanted to have a submersible robot, and they wanted to be buoyancy neutral at certain depths. And therefore, of course, this wouldn't do that. It needed to have a surrounding plastic membrane and some other things put into it. But you know, ultimately, you know, you could not have that strength and create this according to their requirement in any other way. Some other things that are pretty cool. This is a tree and a doll's chair. But the point of using structures is you use the same material, and the chair is a great example of that same material. But you can have cushion, and you can have you know, the strength in the structure of the chair, so that the doll doesn't collapse on it. I mean, you've got orthotics, which is an interesting area. The robotics company in New York's just raised $6 million with 3D printed orthotics, because of course our feet are all different. So that's getting a lot of traction. Here's it in real life, actually. I was, as I said last week, this is quite a big tree. Of course, it was not printed as one piece. It's put together. And the skeleton on the right is quite interesting, because that was all printed in a single build by packing it into a build chamber. Of course, bones come apart, separate them, and that all came out of one machine, which had a build platform about that and about that high. Yeah, and imagine it's quite complicated to try and get an algorithm in to ensure there's no impact, and then of course you've got to make sure you know which bone is what. A few other examples from my trip to Germany last week. A shoe. I think he's wearing a football. World Cup's coming up, and apparently they're using that football. No, they're not. So just to kind of show you the kind of workflow that goes in to these sorts of structures, and using an example of a hip cap, what is typically done, you break those down into voxels, you select a structure, and you can design these structures according to what you want to have. I'm sure someone in the audience here might be saying, how do you tie it into finite element analysis, which is where you use computer simulation to kind of work out whether things are going to break apart or not. And it's quite difficult to do because there's so many parts involved when you're dealing with meshes. And that's probably the next barrier that these sorts of software, there's a few of them that are going to look to solve, because we need to analyse mathematically how having different structures going together, work within a wider object. So you can imagine you have an object like this, and this bit could be all hard, and this bit could be all floppy. And you could then go seamlessly from one material property to something altogether different. And you can do that with digital materials, as well as using structures, which is a form of digital materials. And then in effect, you apply the various structures, and then you slice it. I don't know how many people are familiar with 3D printing software, but everything in the industry is STL, which is a 3D printing standard, and they're basically hollow surface meshes. And you've got to make sure that they've got no holes in, otherwise it goes to the printer and it all falls apart. There's not been as much effort put in the software of 3D printing as there has been in other types of applications we use generally in the world. And then you get to build the parts, and that process, by putting structures in different locations, has created that structure that is supposed to replicate a natural bone surface. Other ways you can do things are just put a mesh over a surface, bring in the structure, and add the structure, and you can get some really interesting quasi-organic shapes. What's also interesting when you're starting to look at structures and you can change the structure within the structure, the kind of the struts, and this is where you get that gradient functionality, that you can use the same structure. It doesn't have to be a different structure. You just vary how thick, in effect, the lattices are within the structure, and you can have some interesting gradients. So looking kind of beyond properties, and this all gets a bit artistic-y, which might be strange considering we're very, very mathematical audiences. These are, what does it say? 10. They're about 1 millimetre in length and 1.5 15 centimeters long, and it's almost like a material. And this is done with laser sintering. Laser sintering in this case, and this is a nylon. The laser has the accuracy to be able to get to that sort of detail and it to come out and be almost like hair. And it will get better. You can do interesting light for design purposes. This is this was designed in London, and it's actually a kind of wall feature. A lot of money in art, and you're seeing this technology being used by architects now for artistic designs, because it's got a nice touch and feel to it, as well as got good aesthetics. And here's some other sort of material. It's got a kind of armour type structure holding together, and then long nylon. And these are all laser sintering in nylon. This is an interesting structure, fascinating. This cannot be made in any other way. You couldn't, because a lot of structures you could make with your hands. You will never get the accuracy naturally as you'd get with a digital model. And if you look at it, I want it back, so I like to show this one. It's quite fascinating to look at. The great thing, or the thing that I find most interesting about it, I've got no idea what I'm going to do. Yeah. And this is what I'm trying to do here in Silicon Valley, is how can I connect the ability to do this with some people who might have some great ideas? Yeah? Because I'm sure this has a lot of applications if we can't think about it. But I'll share this around, you can have a look at it. And the machine that came off, this ceramic printer, uses the growing out of a slurry, and then it goes into a furnace, burns off the photopolymer, then it fires up to about 1500 degrees and then sinters everything together. And they know down to the 0.001% level how much it's going to shrink. So the resolution is down to 20 microns, which is quite fascinating. This is a structure that was created similar to the one there, but it's in metal, and it has capillary forces. So you can see the water very faintly. Another great side effect, which was just thought about afterwards, maybe it does, maybe it doesn't. And I'm sure that we can get some interesting applications for this if only we could think about them. This is a project from some students in London, School of Architecture. What do they call it? They call it a social recreational space. So you don't need to use your iPhones and your telephones. You can talk to people underneath it. And it's a fog harvester, so you can harvest water. It's designed to have organic structures. It's a sun shield, and this is what some kids, relative to me anyway, came up with by just thinking about what they might be able to do with this technology. And the reason why I like this is not necessarily because it's a sunshade, a very expensive sunshade, I expect. Probably cost $50,000 to make, and on a $500,000 machine. One of the biggest barriers with the adoption and the utilization of this technology is there are things that we can do that we don't know we can do, and as an engineer, you are trained, like I was, to work within the tools that are available. So you design something, you think about CNC. You design something, you think about models. You design something, think about what you are going to make it with. So education is probably one of the most important things, similar to what happened in the computing world. It was not the generation that necessarily putting them together in the 70s. It was the next generation coming on who played games on them that started to break mold and built on that as a platform. And that's what I think will happen with this technology when we get next generation coming through that are unhindered by, you know, the constraints of what we tell them how to manufacture. And they start playing with this equipment, which is really cheap. You know, it's $1,500, $500. You can have one of those on your desk at home, and you can play around with it. And they're going to start playing around with it, and they're going to start trading things that we can't think about today, and start solving some really interesting problems. And I think structures are going to play an important part of that. There's a bit of a debate at the moment. Is it more materials? Is it more structures? I think it's a combination thereof. There's been an explosion of different materials within the REP community, which is the desktop community, PLA, PET, ABS, all those sorts of, and they're putting additives into it to change the parameters. I've got some material in my office which you can make a bag out of. I don't think we've got one here. A bag in the sense, the little money type bag that you would have, I don't know, 500 years ago. You make those little bags that you used to put coins in. And it is, you can mould it, you can scrunch it up. And that's come off a printer like that. The challenge is the quality's not there yet, but it's a great tool that I think the next generation is starting to engage with. Now schools are spending a lot of money on this, and we're going to get more of these sorts of ideas. And as the costs come down, which they are enormously, we're going to do some really, really exciting things. So I'm very close to the end. Lots of slides. Nice pictures, I hope you've all enjoyed. As Greg mentioned, I run the SV4 3D printing meetup, the longest running 3D printing gathering in Silicon Valley. But next week, 27th, it's being held at Livermore. And what you find when you go to Livermore and they do presentations, they speak a little bit more than they should. And you get some really good insight into the stuff that they're doing. So I know it's a bit of a trek. We are carpooling it so that we can get on that fast lane. And we might stop for a beer on the way back. But that's, if you're interested in materials and structures, I can't go into any more detail than that, you know, that might be one that's worth going to. And on a final plug, if I may be so rude, and you'll recognise that, don't we? That's been up for actually a couple of months. I hope that's okay. I'm setting up the first 3D printing accelerator in Silicon Valley. Arguably the US. I don't want to dispute that with anyone, so I won't say. There are hardware incubators around. We know that. My incubator, my partners are here, and we want to get some talent in solving some big problems. Silicon Valley has not been switched onto this technology unless you really look underneath what they did. They backed. So Kleiner Perkins were investors in Invisalign, and DFJ are investors in Microfabrica, but no one really says they're 3D printing because it's not important. We're looking at business applications and solutions. But there's not enough money going into this technology generally to attract the talent to solve big problems. And it is a bit of a preoccupation with software, cloud, big data, etc., biotech and their device. And you know, I'm trying to activate the investment community to start, you know, attracting, you know, the talent with the entrepreneurs and the funding to solve some big problems. So thank you very much, and then I will gladly take your questions first.
Sure, location for that?
It's in Santa Clara. Sorry, I should have mentioned that. My company is in Santa Clara.
The accelerator.
Yes, in Santa Clara. I live here, believe it or not. And you know what HP is doing. It's very, very important to the market to get this technology at a low cost out supported. There's a lot of support needed with this technology. It doesn't work very well. Don't mention it anywhere. It doesn't work very well. It's very, very intensive. Even the desktop, my first desktop computer, I actually made my wife build because I wanted to know if she could do it. She was an English major. I'm a mechanical engineer. I'm expected to know how to build it. But she built it. But it took 3 weeks. And it didn't work. And I couldn't get it working. I didn't get it. Seriously, it's no joke. I got electronics wrong. Yes, sir.
Yeah. So in addition to the printer, you need something like SolidWorks or Libre or one of these, and so your investment in this gets really.
Are you talking about using? You buy a printer, go to Thingiverse and download a whole bunch of stuff and be happy and jolly and have great fun. You know, you can use software like Tinkercad, Autodesk's got some stuff. There's free software that can do limited things. SketchUp, people use that. As long as you kind of know how to use it, you know that if you're trying to create two primitives, yeah, and you want to get them out together, they need to touch. You know, you can't have gaps. And so, you know, if you're not familiar with that as a concept, but most printers now you can bring things in and it's got software that will file fix, and there's lots you can do without going into the software, but a major barrier is how you create content.
Are the libraries of structures and the characteristics available in those, or are they?
You're talking about the kind of mechanical characteristics.
Right.
We will be putting attachments to an FE engine. Yeah, that's phase 2. Yeah, because it's important.
Yeah.
You know, but I think the way we're looking at it at the moment within NetFab, I do more than NetFab, but the way I look at it is you treat the structure as a different material. You would probably go and empirically test that rather than try and run it through. It's called a finite element engine. Basically, for those that don't know, it's an algorithm, I suppose. You know, I did it 20 years ago. I don't really understand a great deal about it. I gave up that. But you know, we're pretty much looking at you go and empirically test it. And engineers will always over-engineer things, especially mechanical. Yes.
You know, what I'd really be interested in, I mean, the commercialization, some of that's going to happen, but you know, the commercialization, the VCs only chase certain things. Like, they want to invest in medicine, they want to invest in breast implants, they want to invest in lifestyle medicine, they don't want to, you know.
They want to invest in money, where money is.
Yeah.
It's not philanthropy, they're investors that need return on capital.
What I really like to see is the Wikipedia of 3D structures, STLs, that are, you know, usable by people, that we can begin to build something that, you know, it can be checked, that quality can be baked into it.
It's called Thingiverse, and it's called the Maker Movement. You know, it's all open source. There's 500 copycat from the RepRap movement, which occurred in 2008 when the FDM process, the extrusion process, came off patent, and then was it Adrian Barrett, University of Bath, basically cobbled together the first RepRap, which could in effect print itself as long as you went down, be it Home Depot and bought the nuts and then you got your motors, etc. You know, so it's already there. The problem that you get with that ideology, and it's a great ideology to have, is it doesn't attract the investment. And you know, that's why the US government, you know, has already put in at least $240 million into this technology. And there's another $1 billion that I believe still going through Congress, you know, because it's an international race. You've got Europe, UK government alone allocated 600 million, which is relatively small compared to the 1.2 billion per capita. Is more. The Chinese government and big companies are putting in $500 million plus. But GE's allocated a lot of money to this technology. So, yeah, all great stuff, but it doesn't attract the investment. Yes, so we've had one for you. Can I go to you first, please?
How does scanning relate?
Well, scanning is related as it's creating content, digital content. There's three ways to get content. Call it get. One, you scan it. Two, you start from basic principles, primitives, and build up like a CAD model, or you download it, and someone else has created it. Most people are not creative. I'm not creative. You know, I buy a car, and you know, I choose what car, but I know that I want to personalize it. I want to have the wheels that I choose. I want the color I choose. I want a whole bunch of extras. So I think that'll be probably the norm in the consumerization side of it. It's like the iPhone cases. You can get iPhone cases printed out that are personalized in the sense that you can drag and drop stuff, and it's cool, $30, what's that, etc. That's all good, but you know what's really more important, arguably, is us. We're all different. You know, if you look at the biotech world, I've invested in biotech. You know, it's all about personalized drugs. You know, Herceptin's a classic example of that, you know, for breast cancer. You know, they test you first before they give you the drug because they can work out whether or not you can get it, proteomics, all that. It's all about personalization. And same with medical devices and wearables. You know, sensors are huge here. Everyone's banging on about the. You know, people heard of Project Ara, what Google are doing, using 3D printing now. To have modular type designs to your phone, and you slot in things and sensors and all that, and you can colour print, 3D print your own personalised shell to it and all that sort of stuff. So personalisation is on the rise, and it's been that case for many, many years. Just look at the fashion industry, the high turnover. People want to adapt what they've got and change it quickly and have it personal. So I think that you know that is a trend, and medical being a high value product is where we'll go first, and it's already going there first. Aerospace is always going to get a lot of money because it's called, you know, the government defence budgets, isn't it? And that filters into the commercial world. Sorry, I bang on a bit too much. Yes.
Yeah, for the 3D printing software, what are the typical program languages used to use?
Program language. NetFab's in Pascal, actually, believe it or not. I know. I complained last week when they told me. But apparently it's very easy to learn. I had a conversation with someone earlier on today, and they said actually it's pretty easy to learn if you're a software person. Skype was done in Pascal. I think it's a European thing. He's conservative over there. Come on, you know. Called imperial decline. Yeah. You know, we don't like to change quickly.
So I'm very interested in the software perspective. What
Beautiful.
are the challenges?
Challenges?
Could you give us an overview of the status of the software?
Yes, delighted. Challenges, I haven't got the talent to solve the problem, so solve the problems. Yeah, seriously, it's been overlooked. Don't forget, a lot of the guys that have been developing this, the hardware, it's always been focused on the hardware. They're not software folk. So we do need it to be simplified. It's very difficult. Even the easy stuff is relatively difficult. I don't know if anyone's come across a company called 6 Sense, another kind of little plug. You know, I advise them on 3D printing, and they're using their Razor Hydra, which was a portal to. I'm not a gamer, but you know, it's interesting. I advise a company that's in games, and their games company, they developed a virtual reality environment on which you can design using games control like Wii's. It's called a Razor Hydra, and they've got a STEM system coming out, and it uses magnetic precision technology to get 1% angular degree, irrespective of whether there's something in between. And it's fascinating that you can design objects with a full CAD engine behind it by just doing this. Whereas typically, you've got to be a rocket scientist to open up SolidWorks, because it takes a long time. I don't know how many SolidWorks people in the room. People can use it. It's tough, isn't it?
Yeah.
Really tough. God. NetFab's much easier, believe me. But there's others. You know, there's Autodesk doing a lot of work in this space. Whether there'll be any Autodesk people in the room before I give an opinion. Autodesk, come on, put your hands up. Okay, good.
Were you talking about 6 Sense that's on Google Code? It's an open source project?
No. Sixth Sense. It's called Sixth Sense Entertainment.
Oh, okay.
Yeah. No. Sixth Sense Games Company. Where was I? Oh yeah, Autodesk. They bought Tinkercad, which was a very well marketed, venture-backed company actually, but clearly, there was no money in the consumer market. Consumers are not prepared to pay much money for software, so that's the problem. That's the reality. There's a catch-22, isn't it? Develop software, and who's going to pay for it? Yeah, it's a problem. Software's a challenge. Designing, creating content, other things that are out there. You've got Autodesk, you've got Blender, you've got Rhino. They're all very good design. They're very difficult to learn typically, and they don't necessarily match well with 3D printing because they can be full of holes. So they need to go through some sort of file fixing so that it's solid. So when you do send it to a printer, you've got a high chance to get the output that you want. But Adobe, anyone picked up on the 3D printing button on Photoshop? They didn't make much of that, did they? You picked up on that? You have a question. The 3D Adobe have a Photoshop button, a 3D printing button within Photoshop, and you can define the printer and you can print it, and it's for that printer. Of course, they're going to be interested in color, which doesn't work generally in 3D printing. Yes.
So, in regard to the software challenges, you were showing us quite a complex 3D printed object there with a capillary action.
Yes.
Fluid in there. So you're saying that do you have software that can actually calculate that capillary action?
It'd be great to have that.
Yeah,
those sorts of things. There's quite a lot of simulation software in thermodynamic and fluid flow and finite element analysis. I remember all this sort of nonsense going back 20 years. These really important things. Especially if you're trying to get fuel into a jet engine efficiently, for example, you've got to make sure that that little thing can last for 20 odd years and be as efficient as possible. And so those sorts of tools are available. It's very much tied to traditional manufacturing. So what we need to do is bring those sorts of skills and solutions in and tie it into this sort of technology. But it's more complicated if you've got lots of different structures. Doing solids, which are pretty easy to map out and do your analysis on, is much easier than trying to do it on this. And especially on this, if this might be moving, which you might want it to move because it serves that purpose. So it does get more complicated. So 3D printing will require more horsepower. And of course, when we start digitizing the world, we're scanning, which we will be using these at some stage to be doing 3D scanning. There's no doubt about it. Why wouldn't we? That is going to just create an explosion of new servers. Yes?
So, the way you can go to Walgreens or CVS and get your photos printed, you think it won't be too long until we go to a hardware store and get hardware stuff printed, or a toy store and get toys printed? Or
I think it's probably a matter of when that you'll be given the printer by Home Depot or Lowe's, and you get a license to print out so many tools. So your shed's gone, and they'll charge you a license, for example. Whether we will have every type of printer in the room, because there are so many of them, and I think what you'll find is, like we find today with printers, certain printers, 2D printers are used in certain environments, certain other ones are used. Computers are the same to a degree, aren't they? Not everyone has a mainframe type server stack in the house. Some people do, but not most. So I think every similarly in manufacturing, every manufacturing of a product has a specific piece of machine for that. I suspect for the short term, yes, we will do that. But as we might use structures more and get into more biomimicry, as having less materials, which is what I was talking about, and having more structures to replicate the materials and putting additives into the materials, to add different conductivity or thermal conductivity, electrical conductivity, might mean we end up just having one sort of material and one type of printer, almost like the Star Trek replicator, you know, which is where the rec-rack movement kind of got its name from, or the MakerBot got its name from. I don't really know. Maybe I'm a dreamer. Yes. Yes.
I might have missed that if a bioprinter is included in 3D printing. Bioprinter.
Bioprinter.
So could you give us any comments on bioprinting?
The Affinia is good because it's reliable. That's why I resell it. The MakerBot's got the brand. There's one Kickstarter called the Micro Printer. I think it was $199. You know, and it's going to be $300. Pirate was another Kickstarter, which Kickstarter's been amazing in bringing these low-cost printers to market. It's difficult. You know, there's 500 of them. Which one do you choose? You know? Do your research, find your budgets, and work within your budgets. And you can buy some really expensive ones that don't work very well, and you can buy some really cheap ones that don't work very well. And then vice versa with regard to good ones. It's mixed, and it's probably, you know, those guys that were around, you know, in the 70s, you know, really around. Not like me, I was in shorts. You know, there was a lot of people doing computers, weren't there? That's correct, isn't it? A lot of people putting things together in a garage, and that's a similar case today. And there won't be as many in a few years' time, especially when the likes of, you know, HP coming in and, you know, Autodesk coming in, you know, Google's making phrase in, you know, who knows? Any other ones? I don't know how long we've got. It's now 8:15 and you've got networking. Yes?
I saw a YouTube video that a printer actually printed a house, a temporary house has a like earthquake or something. Do you consider those as 3D printer too, or like?
Yeah, I can, because, you know, it will come. And there's a professor down in the University of Southern California that's doing it using concrete. Berkeley are doing some stuff in this space as well. I think for the likes of disaster relief and those sorts of things, because there's a lot of dollar there. I used to do, that's the kind of thing I did in the army as well as blowing shit up. I would go and construct temporary camps, and that's what we did in Bosnia. You know, you go and troops move in, and you bring Corimex, which are basically containers, flat pack that you pop up, and you know, it would be great if you could just bring a machine and use the local sand, add a little bit of magic powder, and get a gantry going around. It'd make my job easy because I haven't got to have 30 vehicles carrying a load of, you know, flat pack housing. So I think yes, possible. You know, the first 3D printed house is a bit of a cop out. It wasn't really 3D printed. It was using they brought a laser cutter onto site, and they put those bits together, and that was actually in a country called Denmark. So yeah, possibly. It's too expensive at the moment, but as the costs come down, yes.
You know,
Yes.
Just a comment, that's a very interesting analogy where insects actually build their nests, like they use the earth and build their termites.
No, I use that analogy quite often. It's like, why are the walls straight? You know, if you look at the adobe house and you look at ants, you know, the reason they're straight is because that's the way we can actually build them. And if you look at steel, the classic example of how we use steel in structures, you know, you have steel that is, you know, it's a panel for the boat, otherwise it will sink. However, the steel in the corner, there's an I-beam. And not only that, it's got a different carbon content because you need different properties. So, you know, what I'm talking about when I say you can have structure, then you add an impurity or some sort of additive, I'm kind of using the analogy of adding carbon, and then you have different cooling techniques that give different. So, you know, we're starting high on structures, and what was mentioned earlier on is the low level. We're kind of somewhere in between. Yes?
Rather than small, is there such a thing as a giant 3D printer that uses, say, concrete to
a layer up and build something?
Yeah, this chap in University of Southern California, that's what he's been doing, and it's a big gantry, and it's got a pipe. It's a bunch of stepper motors, in effect, big stepper motors. But what's important is not so much that you can control a nozzle which might be that thick. You need to design the nozzle so it lays it down in a way that allows it to hit the previous layer without destroying it, and also you need the previous layer to set quickly, as well as not to set quickly, but also maintain its form. And so what they do, they put fibres in it. It's almost like the way they used to build houses many years ago was to put straw into it, or they'd put horsehair into it. So they're kind of using that sort of thought to apply it, so it can support the next layer, because it's all about being able to support the next layer, so it needs to settle very quickly and strengthen. Thank you for listening.